today is number 40. So the quiz problem. Is number 40. Okay. So and it's about more rational canonical form stuff. Okay, so let's just kind of recap what happened last time. Okay, so
real quick, Taylor. Today is fine, I think, for the other classes, but maybe going forward, would it be possible to have the quizzes on a different day than Friday, just because it usually ends up being when combinatorics and complex are due?
Yeah, I think we could probably do them Monday, I guess.
And I don't know what everyone else would think about a particular day, but I know we've talked about it.
How about you guys have a discussion on what day you want to have it, and then we'll have it that day.
Sounds good.
And also, there's a reminder that we have an exam coming up. So that'll be like a weekend exam like we had last time. So I think that's next week, if I'm not wrong. I'll double check and then post in the chat, but I think it's next week. Okay. Yeah, and so you guys find a date that you like for the quizzes, and we'll start doing it on that date.
Appreciate it.
All right. So let's just kind of recap what happened last time. Oh, I'm on page 2. Okay, well, all right. So last time, by the way, there's a little, Keith pointed out to me that there's a little lock on the bottom left of this app. And if you unlock there, you can flip back and forth between the pages without moving my pages. I just wanted to let you know that. So it's this little lock here. So I guess I could do this. So I'm going to lock so that you guys can see. But so last time, what did we do? Okay, so we talked about like multivariate polynomial division. And one of the motivations was, so we had this map here, right? And the image of this map is the rational normal curve, this kind of famous curve. And we wanted to figure out what the equations of this curve were. We had some candidate equations, right? Maybe we thought that this was maybe the ideal here, right? And we wanted to check that, we wanted to solve the ideal membership problem for this thing. We're not quite at showing that this is the ideal of the image. We need elimination theory for that, which will probably be the class after this one. But we were able to show this ideal membership. And what we did is we introduced polynomial long division. Okay, and polynomial long division depends on a term order. So it's a ordering of all the terms. And the terms are, well, the terms are these things, these basic terms like this, okay, so there's different term orders that you can use. Okay, once you fix a term order, then you can start to do polynomial long division. Okay, and polynomial long division kind of proceeds as usual long division, except for after you're unable to divide by one thing, you go on, the thing that you're dividing by, you move on to the next one, and you just kind of match the leading coefficients, and the leading coefficients are done with respect to your term order. What was interesting about this is that, okay, so at the end of this procedure, this algorithm, what you'll do is you'll get, a number of terms, one for each element of your basis that you're using. So this isn't a basis as a vector space, but this is like an ideal basis. And then you'll get these F1 and F2, and you'll get a remainder such that you have this. This is actually, you can do it with more than 2 generators, but we did this example with 2 generators. The other interesting thing is that this is highly dependent on the term order, right? So like, if we did this term order where we did this polynomial division where we used a term order where this term order here, where we took z to be, so we did lexicographic with z bigger than y bigger than x, then the algorithm gives you an interesting output. If you do it with another term order, so you say that x is bigger than y is bigger than z, then no division occurs, since the monomials of the leading monomials here don't divide the leading monomial of the thing that you're trying to divide into. And so this gives you a remainder h. So the point is that, okay, there's something going on, right, where like in one of these cases, there's an interesting result where we get, we can prove ideal membership by showing that the thing that we're dividing is a combination of the two generators. In the other case, where you switch the term order, the remainder just output h. And so the idea is that we're going to have to kind of like fiddle with this algorithm a little bit to make sure that that our output's going to be well defined, and that we make sure that we're dividing by nice things. And the nice things that what'll happen is we'll kind of modify the generators of the ideal so that they become a Groebner basis with respect to the term order that we're doing. And in that case, you can guarantee that division, this division with remainder procedure is always going to determine ideal membership. In particular, when you have a Groebner basis, right, your remainder will be 0 if and only if the element is that you applied the division algorithm to is a member of the ideal generated by the elements in that Groebner basis. Okay, and I'll say this again. All right, so all right. So let's go back here, and let's kind of lay out some of these things here. So, all right. Okay, so what is a Groebner basis? Maybe we should start there. Okay.
I was about to ask that.
Yeah. So let's say a definition of a Groebner basis. Okay, so definition. Okay, so fix f a field, and I an ideal in f of x1 through xn. So this is the general setup. We're talking about polynomials. Okay, so this is about multivariate polynomials. Okay, so a collection elements G is equal to G1 through GR, a subset of I, is a Groebner basis for I, if and only if, well, one, I is equal to the ideal generated by these things. And two, the initial ideal. So this is the ideal generated by the monomials here. So this thing is equal to the initial ideal of G1 GR. Oh, I can't do that. Okay, wait. That's I've been using parentheses. So do I want to use angle brackets or do I want to use parentheses? Maybe I should be using let's use angle brackets today. Okay. So okay, and so what is this thing? So here, okay, in this expression here, in I is the ideal generated by in F for for f and I. So this is a monomial ideal. So it's generated by monomials, which is the leading term. Okay, so it's generated by monomials, and these things here, these are the same things as the leading. This is the leading term. Okay, so like if we were going to go back, let me go back here for a second. So the leading term are these are the leading terms here. Okay, in the particular order. So in particular, like, so note that so some remarks here is that this depends on a term order, right? So this depends on a choice of term order. Because the leading monomial or the leading term only makes sense if you have if you've fixed a monomial order. Okay. So yeah, so this is two notations. So N is the same thing as LT. It's the same thing as LT. Okay. Okay, so when you have a Groebner basis, okay, so there's some big theorems that we have to say that I just want to get out of the way, and then we'll start using them. So the big theorem, right, is that if G1 to GR is a Groebner basis, for I, which is an ideal in a polynomial ring, then so this is again with respect to a term order. Then F is an element of I if and only if Rg of F is equal to 0. Okay, and so this is the remainder after division by G1, G2, GR. Okay. This is the one thing that I wanted to say. The second thing that I want to say is that so the order in which you divide doesn't matter. So so the order divide doesn't matter for a Groebner basis.
Can I ask a question?
Yeah.
Seems like you would just take, if you want leading term monomials, seems like you would just start with those, but then maybe your span isn't big enough. Is that why you might not just do that? Or
so like if you just took leading terms of the generators?
Yeah, like if you're so I is the if you're G1 through GR,
Yeah.
why would you pick anything but monomials for those? Maybe I'm not asking.
Well, not every ideal is a monomial ideal. So you can't make it so that everything is just made up of a single term. Is that what you're asking?
Almost. It's if you took linear combinations of those. Well, never mind. I take it back.
No, I mean that's a fair question, right? Is it possible? Are you asking like, if I have any ideal with polynomials, is it possible to make it so that they just look like x, like products of x's and y's and z's with no sums in them? Is that a possible? Is that what you're asking?
Well, when you do the linear combinations, though, then you get the sums and stuff, though, right?
Well, you do, but it's not true that you can always find a generating set of monomials.
Okay. Okay.
Right? Yeah. And those are, yeah, so those are special ideals called monomial ideals, which Spencer is a big fan of. Yeah. So, but yeah, it's not true that you could do this. Yeah.
So when you say
This is for Groebner. Huh?
is that remainder after division by all of them, or each of them don't give a remainder after division?
So division is a process where you take a list of elements, right? And then you will end up getting a bunch of coefficients and then a remainder. So division is by definition a process where you input a list of polynomials.
So that's division by all of them, yes.
Yeah, division by all of them, right? Just division by one of them makes sense. I guess division by one of them could make sense because you just apply the division algorithm. Yeah. So this is by this set here. Okay. But so note that a priori, so let me just give some warnings. So first, when we write this thing, we actually mean we actually want this ordered. I'm only writing this set notation because we've already used round braces for ideals, right? And I didn't want it to be confusing. So it really depends. So a priori, when we input these bases into these division algorithms, the ordering matters. Okay, so if it's not a Groebner basis, the order matters. When it is a Groebner basis, you can permute these, and the result of this division algorithm, the remainder will be the same, right? But that's not true when you're not a Groebner basis. And I didn't prepare example, but they should have some in the book. What else did I want to say? So this solves the ideal membership problem. Yeah. Again, this is all with respect to a term order. And I think that's all I wanted to say about this. Okay, so this is kind of the important part here. So this solves this ideal membership problem. And so so one of the big questions is how do you find a Groebner basis?
Okay, cool. That was literally about to be my question, Taylor. I was like, you say this solves the ideal membership problem, but we need a Groebner basis.
If I can't produce the
yeah.
basis. So how do you find a Groebner basis? Okay, so all right, so there's these things called syzygies, right? Okay, so it has to do a lot with two things. So there's two important things. Okay, one is Buchberger's algorithm or criterion. And I don't know if I'm saying his name right. And then there's Buchberger's algorithm. Okay. Okay. So okay, so there's also another thing that I want to say, but maybe we'll do that later. I was going to give there's kind of a useful fact about kind of a characterization of these, but let's just give these things first. So to do this, I need to tell you what a syzygy is. Okay. So okay, so we need. Okay, it's a good Scrabble word. Syzygy. Okay, So what is a syzygy? So by the way, what is a syzygy? So a syzygy is actually it's an astronomical term. It's a straight line configuration. Configuration of 3 or more celestial bodies. So like an eclipse is a syzygy, okay? And so what is a syzygy? Okay, so so a syzygy is the thing you use to kill a leading term of two things. So so S of FG, well, this is equal to AF minus BG. Okay, where A and B are monomials designed to kill the top term. Okay, so like there's this operation where I can do this. So okay, so what does this mean? So A is the least common multiple of the initial of F, the initial of G, divided by the leading term of F, and B is the least common multiple of the initial of F, the initial of G, divided by the leading term of G. Okay, so I kind of like to think about it this way. These formulas, you never really use them. Maybe you can use them once or something, but after I do it, you'll kind of see what we're gonna do. So let's do an example of a syzygy. So let's do an example. Okay, so so I had an example that I'll need later. So where is my red? Here we go. Okay, so let's do an example. Okay, so let's do, so use the term order. So use the lexicographic order where we take Z bigger than Y, bigger than Z, X. Sometimes this is called reverse lexicographic, but okay, so we're gonna do it this way, okay? And so let G be this set, G1, G2, where we're gonna go back to our rational normal curve example. We're gonna do Z minus X cubed and Y minus X squared, okay? So then the syzygy of G1 and G2. Okay, so this is what we'll do. So we're going to do Z minus X squared minus, okay, something times Y minus X squared. Okay, and so we just want them to kill the leading term, so we just match them. So I'll put a Y here, and then I'll put a Z here. So the idea is that, you know, this and this and this, these kill each other.
Do we want the first parenthesis there to be Z minus X cubed?
Yeah, we do.
Oh, thanks.
Yeah, thank you very much. Yeah. So yeah, so we've kind of, this is the A and this is the B that I had in this expression, right? Okay, so they kill the top term, and so what do we get? So this is equal to so minus YX cubed, and then plus ZX squared. Okay, and so if we're going to write this in its term order, it's ZX squared minus YX cubed. Okay, so that's the proper way to write it. Okay, so this is the syzygy of the two things. So you have this thing, and notice that you have this kind of like new leading term, right? That's the idea, is that it's a way of producing the new leading terms. Okay, so these are the syzygies. It depends on a term order, and now I can go back to this now I can state the criteria. Okay, so the Buchberger criteria is the following. Okay, so the set G is G1 through GR is a Groebner basis. If and only if for all ij, for all I not equal to j, the remainder after division of the syzygies is 0. Okay, so this is a big one here. So if we can prove that the remainder after division is 0, then we get a we get a Groebner basis. Okay, and then the algorithm says, well, you can guess what the algorithm is going to do, right? Well, what we do is we'll just repeatedly, if we don't have a Groebner basis, we take syzygies, right? If it's if it's not in there, we throw it in. Okay, it doesn't change the ideal because so note that so note. So maybe I should write this back up here by this thing here. Note that if f and g are in an ideal, then s of fg is in the ideal too. So by taking syzygies and throwing in syzygies into or throwing in remainders of syzygies into a set of ideals for a generator, you're not going to increase the size of an ideal. Okay, so the Buchberger algorithm.
Is that because the coefficients are polynomials, and when you do linear combinations?
Exactly. You're allowed to do linear combinations of any element in an ideal, and it remains in an ideal. It's the closure property of ideals. Exactly. Yeah. So okay. So we can obtain a Groebner basis by repeatedly joining RG, SGI, GJ, to get to iterate on your basis. Okay, so what you'll do is so this process will terminate. So you take G1, G2 to GR, and then what you'll do is you'll get a new basis where you do G1, G2, GR, and then you just start taking syzygies. So you do SG1, so you do, so this is, let's say this is a G naught, right? Okay, so then you do R G naught, S G1, G2, R G naught, S G 1, G3, etc. And then you kind of keep going. So it's really big. G2, G3, right? And then you all the way down to you have RG naught, S, G R minus 1, GR.
Apologies, probably just said this. What's the G naught?
G naught is this original Groebner, right? And this is G1. Okay, so like you can just take syzygies, take the remainders, and just keep adjoining that until it becomes until it's closed under syzygies. The generators are, you know, like you take a syzygy, you do division, and until you hit Buchberger's criteria, you go.
So there's like choose 2 of those possible syzygies that we would take.
It's a pain. Yeah,
that's a lot. Yeah.
It's a pain, and so we do computers a lot for this. But you guys should do a couple examples by hand. But then, you know, after, you know, but when you get to big computations, you use computers. Yeah. Also, this algorithm. So what do we know about the complexity of this sort of stuff? So the polynomial division algorithm. So if you do it over a finite field, so over F2, you can prove that polynomial division is NP complete, right? And you can prove that the polynomial division in, I think, over the integers or over the rationals is like p-space complete. So they're kind of like, okay, so there's a lot of these like complexity zoo things that have to do with the you know, PNP, and there's a whole sort of zoo of complexity classes in computing. And it turns out that polynomial division is one of these places where, you know, if you can prove things about the complexity of polynomial division, then you'd know a lot about complexity classes in general. Anyway, the runtime of these is not the best, but it's useful enough that we still use it. Okay. So there's so this is the algorithm here. Okay, so let's go back to this example here. Okay, so we have this syzygy, and so what we'll want to do is we'll want to test if this is a Groebner basis. Okay, so back to our example. Okay, so let's see if this is a Groebner basis. Okay, so by Buchberger's criterion, we have this thing here. So we did y minus x squared z minus x cubed is a G basis. I guess let me do it in the right order. But the order won't. Okay, so spoiler alert: this is a Groebner basis. Is a Groebner basis. Okay, let's call this thing G. If and only if. So RG of the syzygy, let's call this G1. Let's call this G2. Of G1, G2. Okay, so this is this is 0, and this is RG of. Okay, and now we're going to take, what was it? Z x squared minus y x cubed. Z x squared minus y x cubed. Okay, so let's see if this is if this works. Okay, so let's do the division. Okay, so here we have z x squared minus y x cubed, and I'm dividing by our two elements. So we have z minus x cubed and y minus x squared. So this is G1, and this is G2. All right, and now we're going to do this thing where we do division with remainder. Okay, so we already have a match, right off the bat. So this thing matches with this one, right? And so what we do is we just kind of complete it. And so we get z x squared minus and then we have x to the 5th. Okay, and now we subtract. Okay, when we subtract, we get minus y x cubed plus x to the 5th. All right. Now we do the next round. So this is how we got this term here. Let's do the next round. So the next round is we're trying to match up this term here. Okay, so it doesn't work here, and it doesn't work, and it works here. Okay, so so what do we match it up with? So we have minus x cubed. Okay, so now we have minus y x cubed minus, or now we get a plus x to the 5th. Okay, this is 0. Great. So now the process has terminated. And we found that the remainder here is 0. So the remainder of z x squared minus y x cubed is 0. And we also found that, you know, this thing, if we call this h, right? H is equal to f1g1 plus f2g2. Okay, so h is this thing. So we have, so let's just do a little sanity check. Zx squared minus yx cubed. Okay, that is equal to, so f1, which is x squared. And this one was y minus x squared plus, okay, then we had a minus x cubed. And we had a y minus, or, oh, sorry, this is a z here. I messed up. Z minus x cubed. And this is y minus x squared. Okay, so yeah, so this is what we get. So what terms cancel? So the x to the 5th terms cancel here, right? You can see that this thing and this thing cancel after distributing. So, and then you're just left with the leading ones, right? You're left with this and this. Show these two. Okay, so that works out. Okay, so this proves that. So this proves that the set here. So, or this basis z minus x cubed y minus x squared is a Groebner basis for the ideal generated by them. Okay, so with respect to, with respect to the term order, you know, z is, so it's reverse lexicographic, z greater than y greater than x. Okay, this is lex, not deglex, or grevlex. Well, I don't know, the graded, not the graded one. Okay, that's a nice example. So we have a Groebner basis. Okay, what would happen if we did this with another term order, right? What happens if we, so we had that other term order where we didn't have that ideal membership thing, right? So let's see what happens if we start doing another term order. Okay, so let's do the same thing. Oh, do you guys have any questions? Okay, so let's do the same thing with a different term order. Okay, we'll do x bigger than y bigger than z. Okay, so in here we'll take, so we'll start with g0 and we'll start with the same thing. So we'll do, okay, so I'm gonna change signs because I don't want to have to worry about minus signs a little bit. So we'll do x cubed minus z, and we'll do x squared minus y. Okay, so this is our this is a set here. Okay, and we'll call this G1. We'll call this one G2. Okay, so so let's apply Buchberger's criterion. Okay, so we're doing S of G1, G2. Again, this is always dependent on the term order. Okay, and so what we're going to have is we're going to have x cubed minus z plus some crap x squared minus y. Okay, so to get these to match, we just need a 1 here and we need an x here. Okay, so, this is a minus sign. Okay, so this thing is minus z, and then so then we have plus xy. Oh, our friend. All right, so this is xy minus z. Okay, so this is the syzygy of these two things. Okay, and so we saw this. So we in our previous computation, right, from the last class. Well, I mean, we can just do it again real quick. So we saw that Rg of xy minus z is xy minus z. Okay, but let's just do it real quick. So here, xy minus z. Okay, G1 is x cubed minus z. G2 is x squared minus y. And then we have these two things here. Okay, and now we try and match the coefficient, right? So we're trying to match this thing here, okay? And it doesn't work here and it doesn't work here, right? Because x squared doesn't divide this, right? So so this shows us that Rg of, G0, xy minus z is xy minus z. Okay, and so now is where we get into the Buchberger's algorithm type thing. Okay, so what we'll do is we make a new basis. All right, so we'll do G1, which is going to be the same things. So x cubed minus z, x squared minus y, and then we do xy minus z. So I throw it in. And now we need to test, right? So we need to test S G1, G3 and S G2, G3. Okay. So okay. So maybe we'll pick this up at the beginning of class next time. But it turns out that so when you do this computation, right, it'll turn out that the division with remainder here is non-trivial, and then you have to iterate like 3 times or something like that in order to get a Groebner basis, right? So we'll do these. We'll do division with remainder. I think this one. So this one here, Rg1 of Sg1 G3 is equal to 0, but Rg1 of Sg2 G3, this thing's not equal to 0. So then you need to adjoin this. And then you keep going. But it goes to show that like the term order that you pick, right? So like if you're on a qualifying exam, right? If you choose a bad term order, right, your computation can go very long, right? So sometimes you'll get a kind of a hang of which term orders to use, But when you switch term orders, you'll sometimes the computation can be really quick to get a Groebner basis, and sometimes it'll be really long. So I'm going to stop the class here, but I'll stick around if you guys have more questions.
Thanks, Taylor.
Yeah, you're welcome.